So what we're working up to here is an analysis of convention. But before we do that, we have to introduce some concepts first. So what we're going to talk about first is the idea of a coordination problem, because Lewis is going to define what a convention is in terms of a coordination problem. And we're also going to introduce some basic ideas from game theory, because these again are going to be ideas that we use to state the final analysis. So at this stage, we're not going to give a definition of a coordination problem. In fact, that's going to be the point of introducing the game theory tools that allow us to define a coordination problem. Rather, we're going to start by just thinking about some examples of coordination problems. So Lewis has a bunch of examples in the chapter that you read. I'll give you just a few of them. So one example might be that we've arranged to go to the movies together, and of course we have to meet up before we get to the theater. So here our coordination problem is, well, we have to meet somewhere. Where are we going to meet? Another example of a coordination problem is this famous example from Hume. So imagine that we've gone rowing together, we're rowing a boat, and when we go rowing together, it looks like to get anywhere, to really get the boat moving, we're going to have to coordinate in a certain way. In particular, we're going to have to row in a particular kind of rhythm. Because if we row in the wrong rhythm, we'll either go nowhere, or maybe we'll go backwards, something equally terrible will happen. But there's a variety of different ways we might row in rhythm. And so again, we face a coordination problem. So exactly which rhythm are we going to row in? One more example, again from Lewis. So imagine that we've gone camping together and we want to build a campfire, and we've got to find some firewood before we can build a campfire. We decide that we're going to go looking in the nearby woods, but we want to cover as much ground as possible. I don't want to go looking in places that you've already looked, and you don't want to look in places I've already looked. That would just be a waste of time. So we need to come up with some arrangement for how we're going to find firewood. Again, this is another kind of coordination problem. The last one we'll talk about is another historically famous one. This one is called the stag hunt. I think it's reasonably famous with game theorists. And it comes from Rousseau. So we're asked to imagine that we're all going on a hunt together, and we have the choice that we can hunt stag. And if we hunt stag, well, that will be a great payoff. Stag will provide us with a great feast if we catch one. But it does require all of us in order to catch the stag. If even one of us decides not to catch stag and instead decides to go hunting rabbits, which we can imagine is the easier quarry, so if one of us defects in this way, the stag hunt will fail. So here again is another coordination problem. We need to decide amongst ourselves, what are we going to do? Are we going to hunt stag or are we going to hunt rabbits? Those are our examples of coordination problems. In each case, we see that there's some decision that we all have to come to about how we want to act together. Now, obviously that's not a definition, but that's kind of a rough idea of what's going on in these cases. To actually go and give a definition, we need these concepts from game theory that I mentioned. You may know this already, but in some ways the term game theory is misleading. Game theorists talk about games, but they're not games in the sense that we mean them when we talk about playing a game with each other. Rather, when we talk about a game, what we're going to mean is that you have two or more people who both face a set of decisions, and exactly what happens in the decision-making scenario, exactly what they get for doing what they decide to do, is crucially dependent on what the other person decides to do. So as we'll say, a game is some situation with at least two people where all the people involved have a set of options to choose from. They have to perform some action and they have a menu of options to choose from. And as we said, what I get from choosing a particular option is going to crucially depend on what you decide to do as well. So it's by acting together that we get certain outcomes, not by just acting alone. And we're going to call an outcome just some combination of options chosen by each person in the game. So for example, in the stag hunt example, if I decide to hunt stag and you decide to hunt rabbits, the conjunction of those two options taken by both of us, that's an outcome. And each outcome is going to assign some payoffs to each, what we might call player. Each person involved is going to get some payoff from an outcome. But don't let the word payoff mislead you, because a payoff can be good or bad, just because, well, when we do things together, that might lead to a good outcome, or a bad outcome, or an outcome that's good for me and bad for you, or vice versa. So outcomes lead to payoffs, Payoffs are not necessarily positive. Each person gets a payoff, but it could be a good or a bad payoff. And we're going to represent payoffs just with numbers. A positive numbers for some player is going to represent that the outcome is good for them. A negative outcome is going to reflect that it's bad for them. And the size of the numbers will take to be roughly proportional to how good or bad the payoffs are for each person. So don't read too much into what the numbers are, just beyond that they're there to signal whether the outcome is good or bad, and how good or bad that outcome is. So we now have the basic concept of a game. It's something that involves what we're calling players who have options. A complete selection from each person of an option leads to an outcome. An outcome has some sort of payoff. But it's helpful to get a better grip on this by thinking about a particular example and seeing how it works. And we're going to take a very famous example that I'm pretty sure you'll all have heard of, which is the prisoner's dilemma. So the prisoner's dilemma comes in lots of forms, but we'll think about the original, most sort of basic form of the prisoner's dilemma. So let me tell you about the case first. So we're going to imagine that two members of a criminal gang are imprisoned, and each prisoner is in solitary confinement, so they can't talk to each other. They have no way of communicating with each other. Now, we'll imagine the prosecutors lack sufficient evidence to charge them with the crime, so they want to try and get dirt on at least one of the criminals. So what they decide to do is at the same time, they try to strike a bargain with each of the criminals. And the bargain is this: if you betray the other person, if you say that they're the ones who committed the crime and so give us evidence, you'll walk free and they'll get 3 years in prison. So this is the bargain they give to both criminals. However, they also add that if both of you betray each other, if each says it was the other one who did it, you'll both get 2 years in prison. On the other hand, if nobody says anything, then we'll imagine the prosecutors only have enough evidence to put them in prison each for 1 year. So this situation can be thought of as a game in our sense from earlier, because we have two players, the two criminals. They both have two options. Their options are to betray the other person or to stay silent, to not cooperate with the prosecutors. And there are a variety of possible outcomes. So the outcomes are they both betray each other, they both decide to stay silent, or one betrays the other and the other stays silent. And obviously there are two versions of that outcome. And as we saw, each have different payoffs. In the outcome where they both betray each other, then the payoff for both of them is 2 years in prison. Or, for example, if one of them stays silent and the other one betrays the other person, then the person who stays silent gets 3 years in prison and the other person goes free. So you can see that this illustrates the basic concepts that we talked about before. But to see this a bit better, and also to help us get a grip in a moment of the concept of an equilibrium, we're going to go to the board and we're going to draw what's called a payoff matrix. So we now have on the board a payoff matrix which represents the prisoner's dilemma. Now, again, the name payoff matrix might be a little bit misleading because rather than just representing the payoffs, it actually in fact represents the entire structure of the game, more or less. So let me tell you what each bit of the diagram is doing here. So remember, we have these two prisoners. We'll just call them A and B, so that those are their names. So the first thing to notice is that the diagram, because it's in 2 dimensions, going horizontally and going vertically, represents both of the options that are available to each person. So for instance, focus on A, person A. Here we're writing the options that are available to A on the vertical. So we're saying that A has 2 options: stay silent or betray. So we should read the rows as representing that A performs a certain action. So this row corresponds to the action of A staying silent. This row corresponds to the action of A betraying the other person. And of course we do the same thing for B as well. So here on the horizontal, we're representing the options available to B. And as we said, they're both offered the same options in this case. B can stay silent, or B can betray the other person. It's worth noticing that it's not the case that in every single game the same options will be available to the 2 players. But we're going to stick with a simple example where they are. So the columns correspond to the actions available to B. This column represents the action of B staying silent. This one represents the action of B betraying A. And remember, we said an outcome is basically just putting together a choice of option for each person in the game. And that means that each cell is going to correspond to a particular outcome. So this cell is the outcome of both people staying silent. This cell is the outcome of both people betraying each other. And these cells are both cells which have an outcome where one person betrays the other. So in this outcome, A betrays B and B stays silent. And in this outcome, B betrays A and A stays silent. So each of our cells are outcomes in the sense that we mentioned earlier. The final information that we have on the grid are these numbers, and these are the payoffs. So you'll see that in each cell we have two numbers, and that's because we want to represent the fact that both people are getting payoffs. The outcome has some impact on both people. It's bad or good for both people. And our convention will be, in this diagram, that in the upper right-hand corner of a cell, we'll write the payoff for B, and the bottom left-hand corner will write the payoff for A. So then what this means is, in the outcome of A staying silent, B staying silent, the payoff to A is -1, and the payoff to B is -1. And here we're just taking the numbers to represent years, or the numbers are directly proportional to the number of years. So -1 represents 1 year in prison. Again, we're representing 1 year in prison. Let's look at some other outcomes. So in the outcome where they both betray each other, again, they both get payoffs. They both get negative payoffs. A gets -2, B gets -2. That means they're both going to prison for 2 years. These other cases are maybe more interesting because one person gets a positive payoff or a non-negative payoff and the other person gets a negative payoff. So 0 will represent us going free and -3 will representing us 3 years in prison. And so this cell represents the fact that when A betrays B and B stays silent, then the payoff to B is -3, 3 years in prison, and the payoff for A is that A goes free. You'll notice that it's the same numbers in this cell, just flipped, and that's because the payoffs for each person are flipped in this cell. When B betrays A and A stays silent, B goes free, i.e. gets 0, and A gets -3, i.e. 3 years in prison. So this illustrates all the concepts we talked about before. The horizontal and the vertical, these both represent the players. The rows represent the different actions open to player A, and the columns represent the different actions open to player B. And if we had a more complicated game, where the players have more options, we would have more rows when A has more options, and we'd have more columns when B has more actions. But since we each only has 2, that means we have a 2x2 grid in this fashion. The other thing I might mention is that in theory it's possible to have payoff matrices involving more than 2 players. But to do that, we'd then have to start working in 3 dimensions. There are actually some examples of grids like that, payoff matrices like that, in the Lewis chapter. But as you'll see, they get kind of harder to read and they're definitely very hard to draw. So these kind of have a limited usefulness once we go beyond 2 players. But that's fine for us because we're only really going to think about 2 players. So there are lots of helpful concepts and things that we can do with payoff matrices, but the thing that we're going to think about most in this video is the concept of an equilibrium. So an equilibrium is a special kind of outcome. So these are all outcomes, but some outcomes have a special property that makes them an equilibrium. We'll say that an outcome is an equilibrium if no agent or no person in the game would have done better by doing some other option, holding fixed that the other person did exactly what they did. So a way of thinking about it is an equilibrium doesn't talk about unconditional preferences. It doesn't talk about unconditional preferences between actions. It talks about what action you would prefer to do given that your opponent, the other player in the game, picks a particular option. And an equilibrium is an outcome where neither person would prefer to have done something else conditional on the other person having done exactly what they did. So let's look at this. Let's basically try to find an equilibrium state here to help us get a better grip on exactly what that means. Let's start with the cell where they're both silent. Let's start with the outcome where they're both silent. Is this outcome an equilibrium? Well, to figure out whether it's an equilibrium, we got to take each person, hold fixed what they do, and see, well, holding fixed what, say, A did, Would B have preferred to do something else? If B had known in advance that A was going to stay silent, would B have preferred to do something else than what he actually did in this outcome? If the answer is yes, he would have preferred to do something else, then it's not in equilibrium. If the answer is no, then it might be in equilibrium, but we can't know until we check for every person. So when we're holding what A does fixed, what that basically means is we can ignore this row, because remember we said the rows correspond to actions. So holding fixed what A does means ignoring this row. And we're talking about B's preferences, so we got to compare in the cells corresponding to the different outcomes that are now possible, what are the payoffs to B? And in particular, since there's just one other option, is the payoff to B better when they switch from staying silent, or are they better off staying silent, given that A in fact stays silent? So given that A in fact stays silent, and meaning we can ignore these two cells here, we're just comparing these two numbers. Of course, 0 is higher than -1, and what that means is that given that A stays silent, so given that B's picking his options are going to either lead to this outcome or lead to this outcome, he would actually have preferred to have betrayed because he gets a better outcome, assuming that A is going to stay silent. So this cell here is not in equilibrium. This outcome is not in equilibrium. Because holding fixed what A does, B would prefer to do something else. If B knew that A was going to stay silent, he would prefer to betray rather than stay silent. So the outcome where they both stay silent is not in equilibrium. Notice the situation is symmetric. So it's actually over-determined that this isn't an equilibrium because it's exactly the same for A. So would A have preferred to do something else if he had known in advance B was going to stay silent? Well, here that means we can ignore this column. And we see, well, because if A knew B was going to stay silent, then A knows either staying silent is going to lead to this outcome, and betraying is going to lead to this outcome. And A can see that, well, when they betray, given that B stays silent, they get a better outcome than when they stay silent. So there's a second reason for thinking this isn't an equilibrium. It's also true that conditional on B staying silent, A would have preferred to betray rather than stay silent, so this can't be an equilibrium. Let's do one more example. Let's take this cell here, the outcome where A betrays B and B stays silent. We want to ask, is this outcome here an equilibrium? Well, let's first ask, would A have preferred to do something else, assuming that B does what they actually do? So in this outcome, B actually stays silent and A actually betrays. If A had known ahead of time that B was going to stay silent, would he have preferred to do something else? And here, well, we actually know the answer because we just answered this a moment ago. Because if we are holding fixed that B stays silent, then we're really just comparing these two outcomes. And in particular, we're comparing the payoffs to A in these two outcomes. And we can see that, well, assuming that B stays silent, A staying silent would lead to -1, and A's betraying would lead to 0. So here, they actually would prefer to stick with what they did. So as a matter of fact, they betrayed. If they knew in advance that B was going to stay silent, they would stick with their decision. They wouldn't want to switch to being silent because that has a lower payoff. So what this means is we haven't yet ruled out that this is an equilibrium. It could be an equilibrium. A is holding up his part of the bargain for it to be an equilibrium. But crucially, we got to check with what's going on with B, because the same situation has to hold for B in order for it to qualify as an equilibrium. So to check what's going on with B, we got to see, well, if B had known ahead of time what A was going to do, conditional on what A actually does, would B have preferred to switch what they do? So we know that, as a matter of fact, in this situation, A is betraying. So we can just hold fixed that A is going to betray. In the case that A is going to betray, would B prefer to stick with their original action, and so stick with their original payoff? Or would they have preferred to do something else? When A betrays, betraying for B leads to -2. But when A betrays, doing nothing, staying silent, leads to -3 for B. So if B had known ahead of time that A was going to betray him, he wouldn't have wanted to stick with staying silent. He would have wanted to instead betray. So this means that this is not an equilibrium either. It's not overdetermined in the last case, because it is true that if A had known what B was going to do, he would prefer to stick with what he was going to do. But that's not true for B. If B had known, in this outcome, what A was going to do, he would rather switch to betraying. I won't go through this cell because, in fact, this is exactly the same structure as this case. They're just flipped around. But for exactly the same kinds of reasons, this is not an equilibrium. And the symmetry of the grid should make clear why that is. So let's instead focus on this final case. Is the outcome of both betraying an equilibrium? And by this point, you probably have gotten a sense that the answer is yes. But let's check why that is indeed the correct answer here. So as we know, we got to go through each party and see, do they satisfy a particular condition? In particular, do they satisfy the condition that they wouldn't have wanted to switch if each had known in advance what the other one was going to do? So let's start with A. So as a matter of fact, both people are betraying here. What would A have preferred to do, assuming they knew ahead of time that B was going to betray? So if they knew ahead of time that B was going to betray, that means they're effectively choosing between these two options. And remember we're comparing A's payoffs, so we're comparing these two numbers. So if A knew ahead of time that B was going to betray him, would he have preferred to stick with betraying, or would he have preferred to switch to being silent? And the answer is obviously he would prefer to stick with what he actually does. Because what he actually does leads to a payoff of -2 in this outcome. Switching would have led to a payoff of -3, which is a worse outcome. Okay, so far so good. That's one piece of evidence that this might be an equilibrium. One of the two conditions is met here. Now we got to check what is the situation for B. And of course, the kind of symmetry of the example is going to lead to saying the same thing about B, but let's actually see why that is. So what we're asking now is, would B have preferred to stick with their choice in this outcome if they had known ahead of time what A was going to do? So holding fixed what A is going to do means that B is effectively just considering these two outcomes here. They're just comparing these two outcomes. And in particular, they're comparing these two payoffs, because these are B's payoffs in each of the two outcomes. So assuming and knowing if B had known ahead of time that A was going to betray, would they have preferred to stick with betraying as well? So that means getting their outcome at this cell. Or would they have rather switched and gotten the payoff here? -2 is a higher number, it's a bigger number than -3, meaning that B is getting a higher payoff here. So conditional on A's betraying B, B would also rather betray, because staying silent, given that A is betraying, leads to a worse outcome. So now we have confirmed that this outcome is an equilibrium, because each person would rather stick with what they in fact do, given what the other person in fact does. Given what the other person in fact does, they wouldn't want to switch. So that's an equilibrium. And that's a kind of general concept that we can apply to various different kinds of games. Something that's interesting about an equilibrium is that something's being in equilibrium doesn't necessarily mean it's like overall the best outcome for the players in the game. Because you might argue sort of that the overall best outcome in the game is this cell, because when you add up the number of years spent in prison for both people, the fewest amount of years is spent in prison. In every other cell, more years is spent in prison when you add up the totals for each prisoner. But as we saw, this isn't an equilibrium. And the reason it isn't an equilibrium is because each person has sort of an incentive to do something else, given what the first person does. So equilibriums don't necessarily line up with like the best outcomes in a game, in a certain sense of best, but they instead have a certain important kind of stability to them, in that you wouldn't want to do anything else given your knowledge what the other person actually did. That's what we're getting at with an equilibrium. And it's important to see that is not necessarily the same thing as the best outcome in a game.